So just as a quick reminder, in case you haven't looked at your timetable and noticed words like reception or wine on it, that there will be a brief, that there will be a reception just outside the door from 5 o'clock to 6 o'clock. And so for our last speaker of the day, we're very happy to have Lennart Meier, who will be speaking on topological modular forms with level structure.
Yeah, thank you very much for the invitation and opportunity to speak. So, as Tyler already said, I will be speaking about topological modular forms level structure. So let me say something about the players which are involved here. Before I speak about any level structures, I should speak about TMF itself. And so the basic input is I have a guy called ML, which is the moduli stack of elliptic curves. Okay, if you're not familiar with stacks, I mean, just think of it as some algebraic geometric gadget which classifies elliptic curves. And then there's some magic black box, which I call OTOP, and which spits out a spectrum called TMF. So this is an E-infinity ring spectrum. Okay, I mean, formally speaking, it's kind of a sheaf of E-infinity ring spectra on the entire side of this thing, but I think if you understand this statement, you already knew this. Okay, so so let's say something about the homotopy groups of TMF. I certainly don't want to list them all, but at least some of them. So let's have here pi I of TMF. So here I. So if you have 1, we have a Z mod 2. We have 2, we have a Z mod 2. 3, we have a Z mod 24. And 4, we have a 0, and so on. And if you're familiar with the stable homotopy groups of spheres, this should look familiar, because this is just the same. So, and because it's an E-infinity ring spectrum, we have a map from the sphere spectrum to TMF. And you might think this is a really good approximation, because it has homotopy groups look really similar. Okay, you notice the little gap here. So, but this is not the integers, this is a polynomial ring in one variable. So it's not such a good approximation in some sense, especially what I also didn't tell you is that TMF is periodic. So it has a lot of stuff in negative degrees. So pi star TMF is 576 periodic. So it has a lot of stuff in negative degrees. So maybe it's not so good for an approximation to a connective spectrum. So, but there's some kind of methods to kind of replace by something which is a better approximation of the sphere spectrum. And this is a two-step process. So first, we apply this magic machine called OTOP to a different stack. So the basic idea is that, in general, if you just imagine you have functions on the complex line, kind of holomorphic functions. This is kind of a really big group. But if you compactify the complex line to kind of the Riemann sphere, you only have constant functions. This is essentially what we want to do here. So we compactify this modular stack of elliptic curves, which I denote by this bar, apply this magic machinery, and get a second GAR. Whereas the notation capital T lower MF, as notation it's great, it's not so good to kind of actually say this, but okay, and then there's a third step, namely this guy has still some stuff in negative dimensions, so we just throw it away. So we just say little TMF is the connective cover of this guy. And this map factors like this. And this is a much better approximation. So actually these homotopy groups will be the same, but here we have a Z, and it turns out that the map, so two facts. First of all, pi star from the sphere to pi star little TMF is an iso for star, I think, small or equal to 6. And the second nice feature is that actually also, if we rationalize, or actually it's enough to invert 6, then this is a ring of modular forms. So I mean, in this case, it turns out to be just a polynomial ring in two variables called C4 and C6, which are certain Eisenstein series, which is not so important here. So when I say ring of modular forms, I mean holomorphic modular forms with Q expansion in Z1 over 6. But this is not so important, just some gadget kind of from number theory, which turns up here. Okay, so these are two nice things, and further nice thing about this guy is that it has interesting cohomology, like F2 cohomology, why this is an E2 local spectrum and has no non-vanishing cohomology. Okay, so this is all nice, but then you ask yourself, how do I find out anything about these spectra? And so one method is to go first to topological modular forms with level structure, which are in certain respects simpler, and then go down. So let me tell you something about topological modular forms with level structure. Yeah, this is just repeating the title, I guess, so I'll be brief here. And there's a little bit of pity that there are a lot of different variants of this, and which will come up in this talk, but let me start with one variant. So the general philosophy of level structures is that we don't classify all elliptic curves, but elliptic curve with certain extra structure called a level structure. And one possibility is this, consider this M1n, which is the moduli stack of elliptic curves with the chosen point of exact order 3. Sorry, exact order n. Okay, I said 3 because the example I was thinking about, I want to take n equals 3. So an elliptic curve, so in general this is some kind of scheme with some group structure. So this is the sense at which I mean exact order n. I take a point of this and respect to this group structure exact order n. So to visualize this, it's maybe easiest if we take an elliptic curve over the complex numbers. And you might know that over complex number elliptic curve is just the complex numbers modulo lattice. So if we visualize this, these are the complex numbers, and have some lattice, and this lattice is generated by two vectors, and I look at the fundamental parallelogram where all points lie in because I'm quotient out by this lattice. And so how many points of order 3 do I have here? Let's kind of draw in all 3 torsion points, and the group law is here just by addition, so it will be everything which has maybe not coordinates which are integral with respect to this lattice, but the lattice divided by 3. So I get 9 points in total. Something like this. And then I can just say I choose any of these, which is not this one. So for example, this one, this would be a level structure in this sense, point of exact order 3. Okay, and again, I apply magic machinery and get something called TMF1n. Actually, in this case, it would be a little bit easy, or much easier than in this case. If I'm for n bigger or equal to 2, for n equals 1, I just get the old guy. And I want to say here, n is implicitly inverted. There's some kind of versions when n is not inverted, but this becomes a lot more complicated. Okay, and then again, I can play this game with the compactifications and so on. So I have something called M1n bar, which is compactification. I get something called capital T low MFN, and then I can define, but this is a tentative definition, which I want to change later, that little TMF1n is a connective cover. This is a good definition in some cases and maybe a less good definition in some other cases. So the nice thing about these guys is, or all these guys, that I can tell you a lot more about its homotopy groups in a much easier fashion. So the homotopy groups of TMF are all computed but very complicated, but actually it turns out that these spectra have all, this spectrum, for example, for n bigger or equal to 2, just concentrate in even degrees of homotopy, all torsion free. And this is almost true here as well. And let me give you some examples where I can easily write down homotopy groups. So pi star of TMF1, 2 is a polynomial ring in two variables which I call B2 and B4. And the grading convention is a little bit, so the grading convention is that the degree of BI is a 2i, which comes from some conflict between algebraic and topological grading conventions, which I don't want to go into. And TMF13, I can also easily tell you, it's also a polynomial ring in two variables. Let's say n is inverted, so I have to invert 3 here, and I have a1, a3. And again, the same grading convention. And actually, this is a familiar spectrum. Namely, TMF, if we localize at 2, this is BP2. Okay, this is a little bit of a misleading statement because BP2 is not a well-defined term. This means it's a form of BP2 to speak, but yeah, let me leave it with that. So it's BP2. And actually this guy is also at the prime 3. If you know the degree, kind of how BP2 looks like, you see it cannot be exactly BP2 because the degrees are wrong, but it's pretty close. So I think the statement should be that it's BP2 and then some shift, which I think it's an 8-fold shift, but don't quote me on that. Okay, so at the prime 3. And one nice thing about these guys is that, for example, we know exactly what cohomology they have. We know the cohomology of BP, and we can quotient something, know the cohomology of these guys. Yes, this would be much more plausible. Okay, and as I said, this will actually teach us something about TMF itself, and let me tell you this in the prime 3 situation, something similar for the prime 2, namely TMF smash, and now there's a certain 3-cell complex, which if we want we can write as sigma minus 4 of HP3, so kind of 3 cells, then this is TMF 1, 2. So if we know the cohomology, say F3 cohomology of this guy, as we do, we know the F3 cohomology of this guy, we can deduce what the F3 cohomology of this guy is. And there's a similar story about the prime 2, which is a little bit more complicated. Okay. So this is what I want to say at this point about this kind of level structure. Are there questions about this? Okay, no questions. Next level structure. Okay. So next level structure, I don't actually want to say so much about this. I want to concentrate more on this. I think it's also good to mention this. So there's also a notion of TMF1, TMFN. Actually, kind of what we do is we don't fix one 3 torsion point or one n torsion point, but we identify the whole n torsion with z mod n squared, which is a plausible thing to do if you look at the complex picture. And as I said, I don't want to say so much about this. Just want to say that I get a map like this, and this is a GL2 Z mod n Galois extension in the sense of roughness. So where does the GL2 action come from? Okay, I identify something with Z mod n squared and an action on this, and I just compose with this action. So this means that often if you want to prove something about this guy, you can prove it first on this guy. And there's actually a very nice computation by Vesna-Stoyanovska and Aki Matthew for the Picard group of TMF. So for example, used in the computation by Matthew Stoyanovska of the Picard group of TMF. And I mean, as they started with it, they could also continue to compute the Picard group of this guy, and they all use kind of this Galois descent methods. Right, and yeah, this is just, turns out at the end that this just kind of, so these are the invertible TMF modules. At the end it turns out these are just the suspensions of TMF, so the computation is not so easy, but the result is easy. In this case you have some exotic guys, which are not just suspensions. If I have time, they will come up later stage of this talk. I think this is all I want to say about this at the moment. And maybe it's a good moment to also connect back to what we heard by Agnes this morning, especially for those who actually secretly K2 localized everything I said so far. I know who you are. Okay. So K2 local situation. So for example, we can look at this TMF3 guy, and one can compute that it's K2 localization, and now I write something again which is misleading, is this Morava E theory, E2. So why is this misleading? Because actually I should always write, we have seen in Nico's talk that these things only make sense if I put in a field and a formal group law, and I'm not taking the Honda formal group law but a different one. This is for many purposes not so important, for some it is, and actually, yeah, maybe I don't write it down. Take formal group, so an elliptic curve defines the formal group law, and you take kind of you have exactly kind of up to isomorphism essentially, well, it's more or less true. You have one supersingular elliptic curve at the prime, the prime is 2 here, at the prime 2, and you take the formal group law associated to this. Okay. And as I said, TMF, again prime 2, this is a Galois extension. So in particular, these are homotopy fixed points of this. So we get that this is E2, and then homotopy fixed points G2F3, which happens to be a maximal finite subgroup of the extended Morava stabilizer group in this sense here. Yeah. Yes?
TMF brackets N with no subscript.
This one? Yeah. This is if you take the full level structure, where you kind of choose an isomorphism of the N torsion with Z mod N in bracket squared. Yeah, and actually it turns out that if you take TMF1N, and let's say for simplicity N is bigger or equal to 4, then this is always, okay, now let me be a little bit sloppy and not really specify which kind of version of E2 I mean here. There might be some choices involved. This will be always a product of such E2. And it puts in quotes because, yeah, it might be with respect to different fields there and stuff like this. But it's essentially true. And if we, actually there's another guy, a third level structure, which I didn't speak about so far, which gives kind of one way to kind of realize other finite subgroups here, homotopy fixed points, namely, this is probably bad board work, but I do it anyhow. This is called TMF0N, which is, I mean, you can take this as a definition actually. So I have an action of Z mod N cross on this guy. What is this? I just go back to the definition I gave. So if I fix an N torsion point on my elliptic curve, I can multiply it with an element of Z mod N cross. And this is my action on M1N, and this is functorial enough that I actually get an action on the spectrum, and I take a homotopy fixed point. And there's also a modular interpretation of corresponding stack, which I maybe come to later. And as I said, bad work, let me continue with this. Can you still see here? Okay. And this is, and I put in quotes again because there's issues with the fields of definition, but where these are finite subgroups. Yeah, and I think essentially you can also, they're all cyclic in this case. Okay, so any questions about this?
This is a slightly weird question, but as I understand it, what was called the congruent subgroup problem has a negative answer. So there are these sort of exotic congruent subgroups. Has anybody looked at?
You mean that you look at subgroups of SL2R which are not congruent subgroups? Yeah, so I mean, people have looked at, I don't think, from the perspective of algebraic topology, it's a little bit difficult because you can look at the corresponding quotient of the upper half plane, model these guys, but then to get this rolling, you need something some integral theory first, and then go to the theory of the sphere, so to speak.
But they're all between a gamma n and SL2Z, aren't they? Up to
oh, do you mean this?
Yeah.
Oh, So, okay, what I was thinking about even something more exotic. So they're kind of subgroup of SL2R which are not in between. And these also exist, but this would be much harder. And I mean, I think what you're saying,
Maybe misinterpreted.
you can take some homotopy fixed points of this TMFN and you get a lot of more different things where it might be a little bit harder to say what the actual modular interpretation is, but you can kind of phrase it. It's just a little bit less natural. Okay. So, right. So now I need to erase, and I guess this is an eraser. So I think I gave you some motivation why TMF with level structure is a useful thing if you want to know anything about TMF, and also if you want to understand this subgroups, the kind of more homotopy fixed point with respect to subgroups of Morava stabilizer group. But actually, if I'm honest, this kind of only gives you motivation to consider TMF1Ns for n low, because I said kind of all this kind of descending to TMF business, n does not have to be bigger than 3 or maybe 4. And so I should give you a little bit motivation why it's also good to consider TMF1n for higher n. So why consider TMF1n or TMF0n, or you can also ask them about TMFn for n bigger than 0, which I mean, I guess, n bigger than 4. Okay. And I mean, there's several reasons. I just give you 2 reasons. So one thing is there's a paper by Mark Behrens, Kai Ormsby, Ned Stapleton, and Vesna Stoyanovska, which is a nice acronym BOSS, where they study TMF star TMF, which I think is something one really wants to know, in terms of TMF level structure. Actually, they have several methods to get at this, but this one, so in terms of TMF0n, where n can be arbitrarily big in the approach. So this is one thing, and another thing I want to advertise is, so actually TMF, as said, is an E-infinity ring spectrum. Actually, there's also an equivariant version of this, and was constructed by Jacob Louis in this full strength. And we can do something like so if you have an equivariant spectrum for a group, you can take a fixed point with respect to the group. So let's take a simple group Cn, Sigma group of order n, and let's make our life easy and invert n. So in some sense, it's throwing out a lot of information, but let's try. And even then, we get kind of these guys for arbitrary high n, namely, more precisely, we get for every divisor of n, we get a TMF1k, and to be strict, we have to invert n here as well. So even if you want to compute this equivariant theory, even on spaces with trivial group action, and even after invert n, you have to understand these guys for arbitrarily big k. I mean, if you let n grow. So maybe this is enough motivation, and you could also say that there's, for example, you've maybe heard about elliptic genera. There's kind of a so-called Hirzebruch level n genus, which is tightly connected with the TMF1n. So there are a lot of reasons why one should care about this. So, but okay, maybe let's put this here. There's one word of warning. So, why the computation? Of pi star TMF1n, or say of the, to be more precise, of the ring pi star TMF1n is completely algebraic. And this should be definitely for n bigger or equal to 2, because for n equals 1, I get TMF itself, where it's certainly not completely algebraic. And notice that this is the one number bigger than 1 where I'm allowed to put an exclamation mark after, not changing the meaning. It is quite difficult to do this explicitly. For n bigger than 0. And I mean, in principle, there are algorithms to do this, I think. But I mean, for n small equal to 10, I think it's pretty doable. And then it becomes a little harder and becomes harder and harder. And it's not really realistic to give a closed form for all n. Especially, like, essentially, this problem is that it involves understanding the multiplication by n map on an elliptic curve. And the formula of this become extremely complicated if you really want to understand what happens. Okay, so note that I stressed it's hard to compute this as a ring. And I want to convince you that it's actually not so hard to compute this as additively, and actually even to understand the whole spectrum here additively. And this will be about decomposition. So, okay, so the first result, and it's not really that hard, so I call it proposition, is that, and I guess I always say n bigger or equal to 2 here, because I want to exclude the special case of TMF itself. That, so if I invert 6, this becomes pretty simple. So this is a free TMF16 module. And note when I say free, I mean a sum of shifts of this guy possibly, not just something. So, okay, you can say, oh, but weren't the homotopy of TMF itself complicated? But remember, not if I invert 6. Then these are just polynomial ring, and periodic case here I have to invert one element, but this is completely understood. So it's actually not so hard. So, and you ask yourself, oh, can this be true also at the prime 2 and 3? And the answer is most definitely not. So cannot be true at primes 2 and 3. And the reason is, or the simplest reason is torsion. At the primes 2 and 3, TMF has a lot of torsion. These guys don't have torsion if I don't invert 6 or at 2 and 3. So, I mean, this would be a contradiction. So instead we have the following theorem. So it's formulated in 2 parts. So TMF 1n, if I complete at 2, decomposes into shifts of TMF13 to 2. And there's a similar story at the prime 3. And I mean, this is sometimes we're lucky. We just picked the simplest torsion-free guy we knew, which is related to TMF, and composition this guy. And these are decompositions as TMF modules. I think I don't want to say so much about how to show this. This is, I mean, how I actually show it. I prove a theorem in algebraic geometry first, can decompose in certain vector bundles, first over FP, and this is why I get nasty completions inside. And I'm actually not sure whether it's true without completion. Probably it is, but I don't quite know. And then I use some descent spectral sequence. If you want to prove some weaker statement that's just a summand of the sum of this, then it would be a little bit easier, but we'll not go into that. So you can ask, is there a similar theorem for TMF0n? TMF0n. And the first thing is, so are they similar? And the first thing is, actually, if we invert 6, the story is just the same. So TMF0n with 6 inverted is again is free as the TMF16 module. Okay, so okay, you can say now we are optimistic that this thing can also be true for TMF0n, but no. There's one thing I didn't tell you really about TMF0n, namely, if you take the homotopy groups of TMF0n, there were usually some 2 and 3 torsion, or even 4 torsion. So, and if you have torsion, you can never decompose in these guys. So there's no chance because these have torsion-free homotopy groups. This cannot be true. And actually, I don't quite understand the full situation. But let me phrase, let's say it's a conjecture. It could be also considered as a guess. So I think if it's wrong, it's a guess. If it's correct, it's a conjecture. So let me conjecture something. So let me first complete a 3 and see what I conjecture there. So decomposes into shifts of now I need 2 guys, namely I take TMF itself, 3 completed, and TMF12, 3 completed. So I add TMF itself as another guy. And if I completed 2, I want to have 3 different guys. Namely, I want to have, okay, and this comes now maybe a little bit as, if you have not seen this kind of things before, this maybe looks strange. So I take TMF05, TMF03, and TMF13. Okay, so you can ask why did I actually pick these 5 spectra and nothing else? So the reason is essentially the K2 local situation. I didn't quite tell you the whole story here, but I said this I think I said this, but I didn't really write this. So these F here are cyclic for TMF0n. And actually, if you look at what happens, I mean the most important part is often if you take homotopy fixed points and localize at some point P, then the non-P torsion is usually not so important because these homotopy fixed ones are very easy to calculate. What's really important is the P group part of it. And it turns out that in this kind of thing, if you work at the prime 2, the 2 group part can only be trivial, Z mod 2, or Z mod 4. These are the 3 options. And actually, like for TMF13, the 2 group part is trivial. Here you have a Z mod 2 and here you have a Z mod 4. So K2 locally, I mean, I don't claim I've actually proven this K2 locally, but I think it should be not so hard to actually do this. But at least it looks plausible. I mean, that certainly these 3 guys have to come up. Maybe more, I don't know, but these 3 guys have to be there in any case. And at the prime 3, it turns out the only kind of 3 groups appearing here are a trivial group, which corresponds to this guy, and Z mod 3, which corresponds to this guy. So this is essentially the story. You have a question?
2. There are 2 groups that come up.
Oh, did I say 3?
You just said 3.
Okay, because it was prime 3, okay. Yeah, okay. So this would be maybe not enough to make this conjecture, because I mean K2 localizing is quite a drastic measure. And and so let me take something about evidence. So at the prime 2, this is a known theorem. So true if the order of Z mod n cross is not divisible by 4. So this guy does not show up. Only these guys can show up, and this works. And at the point 3, I mean, it turns out that if Z mod, so yeah, let's tell you when it's known to be true. So true if z mod n3 cross is not divisible by 3. But this is not the most interesting case, because this is essentially the same difficulty as this statement, because we're taking homotopy fixed point between z mod n, with respect to z mod n cross, z mod n cross, and if it's invertible after 3 localization, then it's just the homotopy fixed points are very easy to calculate. And there's one more case I know, and this is joint work with Viktoriya Ozornova. We show it's true for n equals 7, and just to make this calculation for you, this is order 6, which is congruent to 0 mod 3. So this is kind of the first non-trivial case, and we show that it's true. But it's just by essentially by a calculation, which took us some time because we figure out a lot of things. But it's not quite clear what the general picture is at point 3. So are there questions about these statements? Okay, so I don't want to tell you a lot about these proofs, but I want to tell you one step which I find interesting to do these kind of things.
So was it necessary to complete, or could you just localize?
Okay, so in general I only have a proof if I complete. For a lot of n I have proofs when I don't complete. So maybe I come to that later. So because actually there's a similar statements for this compactified modular stacks and connective ones, and there it only works for certain n, but if it works, then it works uncompleted. This is a general feature in algebraic geometry. It's often much easier to get rid of completions if you have something compact. And this was already erased. Okay, but okay, let me tell you kind of one feature of the proof. So the interesting case again is when it's divisible by 2 but not by 4. So let h. So it's not really an example. So remark about proof. Okay, so let h be z mod n cross be congruent to mod 4. Then TMF0n, so homotopy equivalent, I can first take homotopy fixed points, some subgroup H, and then fixed points with respect to C2, where H, order of H is exactly the order of Z mod n cross half. I write this way because this way I don't have to remember whether it's a subgroup or a quotient, but I guess it's a subgroup here. Okay, and this guy, as I said, this guy is easy to understand. If I understand TMF1n, fixed point is easy. So it's really about, so if I get these decompositions, I know all the homotopy groups of this. So it's logical that maybe in the proof it's in there's some step where I actually have to compute this homotopy fixed points first before I do this decomposition, somewhat with respect to sequence. And this follows actually from a general statement. So computation method is the following. Let's call it a proposition. So let R be, let's give it some attributes. So let be then En local, En local homotopy commutative ring spectrum such that the first thing I assume is that pi star R is concentrated in even degrees and should be an Noetherian ring, which is I think only there for technical reasons. The second thing is that I demand the decay and localization, and now I'm a little bit vague again, would be some product of Moivre theories, and I have some subgroup H here, and I assume that H is odd. Or maybe I could do this even more, a little bit more general. I don't really need that H is odd, but it might be, I have this Galois part in the extended Moivre stabilizer group, might be semi-direct product of an odd group with a Galois thing. So it's, yeah. Then I assume that R has a C2 action. And the map from R to this guy is C2 equivalent. So the C2 is the central part of the Moivre stabilizer group, so acts on these guys. And there's a last condition, namely that pi star R, and because it's even, has a complex orientation, and let's say it's too local. So it's too local. I can pick a typical complex orientation and get some VI, and I can look at these quotients, and I demand it's an integral domain for this I. Okay, there's a lot of assumptions, I'm afraid, but this is not so hard to check in many examples. So then, all differentials in the homotopy fixed point spectral sequence for pi star R HC2 are determined and, for example, one gets a lot of information. So if you're familiar with this R C2 graded homotopy groups, one gets, for example, that these groups are 0, and gets a lot of information which is useful. And I should really say this relies crucially on work by Jeremy Hahn and Danny Shi, because I mean they compute what the C2 homotopy fixed point spectral sequence of these guys is, and then there's some tricks how one can actually, if one has this assumption, how can bootstrap from this to get this thing for R. Okay, and what I say, I apply it to this kind of spectrum over there, and almost all things are clear. What one has really show that the homotopy groups are integral domain. This is algebraic, so maybe not obvious, but it's quite well known. Integral domain after a mod out by 2, it's also similar, and then suddenly I'm done. I've computed everything here. And this is the main tool. Okay. Questions about this point?
These assumptions in this product, is the H constant for
No.
each I? Or
No. And essentially what I need is just that the differentials here in C2 homotopy fixed point spectrum are a certain form, and if I know for each sum, and then it's just in general also. Okay. So in the beginning he saw me talking about how important these connective guys are. Well, more or less the first thing I said, you really want to go sometimes to little TMF, the connective guy, but this was all about periodic things. You could ask, and what happens in the connective things, and this compactified things, and whatnot. And at least I want to comment on this, so things become a little bit more complicated there. So maybe I should leave this. Yeah, maybe I'll just start there. So what about this guy is TMF1N. Okay. So it's not really all the same. They're kind of two complications. So two complications. So the first complication is the following. So let's look at the homotopy groups, and again, let's assume n bigger or equal to 2 here. So let's look at the homotopy groups of this guy. It turns out there's a spectral sequence, and you don't have to kind of know all the terms, kind of all the symbols I write down, but there's some spectral sequence starting from an algebraic guy converging to this guy. Okay. Whatever the symbols exactly mean, this is some algebraic quantity one try to compute. This is something one might want. And it turns out that this is 0 for q bigger than 1. So it's just concentrated in 2 lines. So automatically will degenerate. So let me draw a picture how this might look in general. It's even better than just kind of this result. One knows actually a lot about the cohomology. So here I have H0, and here I have H1. And from the form of spectral sequence, you already see that this will all be concentrated in even degrees, because I have this 2p here, and this will all in odd degrees, so there are even no extension issues. And this kind of overlapping means that this is concentrated in p bigger or equal to 0, this is concentrated in p smaller or equal to 1. So this means there can be one overlap. So pi 1 TMF1n, so if you want it algebraically, you could write it as H1 can be non-zero. So which may be either a bug or a feature, but what is more surprising, it can contain torsion. So as I said, this periodic TMF guys, TMF1n guys, have no torsion. This guy can have torsion, but exactly in pi 1, nowhere else. It's a little bit surprising. So let me give you examples of this torsion, just give you a feeling for how it happens. Okay. So examples. So pi 1 TMF 165 has 2 torsion, and this is the minimal example. So it's the minimal n here with just 2 torsion. So you might think, okay, 2 torsion, maybe not surprising, maybe this is just eta, but it's not. So actually eta is 0 in all these guys. There's some new torsion popping up. Okay, maybe I should look at my notes. I mean, I think you wouldn't be able to check it anyhow, but okay. This has 3 torsion, and I'm not quite sure whether it's minimal. I mean, these are, yeah, this relies on some computer computations. And pi 1 times f1, I promise this is the last one I tell you. 82 has 199 torsion. I mean, this prime is so large, you maybe even didn't know that it was a prime. Okay. So this is what happens. So, and I mean, these things are hard. I mean, you really need a computer to calculate these things. There's no closed formula in general, or at least not known. But if you look at this thing that can contain torsion, this kind of theorem cannot be true anymore, because if you have the capital T lower MF13, this has no torsion. This kind of nonsense does not happen there. So it cannot have a decomposition. But it turns out this is the only problem. So if you exclude the torsion, so there's I didn't give theorems a number. Let's call this theorem. Let's call this theorem 0.09. So analog of theorem 0.09 holds if pi 1 TMF1n is torsion free. Okay, so we don't need completions there actually. And let me tell you about the second complication. And this complication is a theorem due to Martin Olbermann, who sadly has left Mouth a while ago, and again Viktoriya Ozornova. So, can you all see there? I think yes, right? So, let's try to look at this TMF0n business again. Let's take the first interesting case at the prime 3. So this decomposes, and I hope I get the numbers right here. So I guess this is the first example I give of decomposition here, which may be bad. So far no surprises. I have one TMF summand, one TMF12, one TMF12, they're all a little bit shifted. But the fourth guy is a surprise guy. So what is this L? This L is an element in the Picard group of TMF. And if I write it this way, not just as a shift of this guy, you can already guess it's an exotic element in the Picard group. It's not a shift of TMF, it's an exotic element in the Picard group of TMF. So this also means in this kind of case, one would have to kind of modify this conjecture / guess to include at least the Picard group elements of TMF, probably something wilder even.
What is TMF? What 1, 2 tensor L?
This is a direct sum here.
No, but I'm just
Oh, sorry.
wondering.
Sorry. This is sigma 12 of TMF1, 2. So yeah, this is a guy which, if I smash up to kind of to the periodic TMF is sigma 36 of TMF, but if I rationalize and stay compactify, would be sigma 12 of TMF. So this is why this must be exotic. I mean, at first we kind of were a little confused because we looked at actually kind of Viktoriya and I proved some decomposition result, but we just knew it was a Picard group element and didn't know which one. And then we talked with Martin about this, and he said, okay, compute the homotopy groups of TMF07, and this just doesn't fit very well with your computation because kind of was not implicitly assumed that this is probably also a shift of TMF. This just didn't fit, but this was exactly because of the exotic elements Picard group, which is, I think, nice. That I mean, it's often nice if one computes the Picard group, sees there are some exotic elements, and then forgets about it again, but they actually come up. Okay, and I should say, then this. Okay, time is running fast. So there's also a similar theorem for this connective guys, if we define them correctly. Correctly means so I said this pi 1 of TMF1n of these guys can be non-zero, but I mean, for many purposes, we would like that little TMF1 as an even spectrum. It doesn't have this annoying pi 1. Then it would be also exactly the ring of modular forms, which happens to be this guy. So there's actually a procedure. So kill pi 1 on this connective cover. I should say this procedure I learned, and probably it's also due to Tyler, how you can actually do this as an E-infinity ring spectrum. So there's some things to check, but then, yeah, you can do this, and then decomposition results work as well, if we have this assumption here that this is torsion free. Okay. Questions? Okay, so I fear I have just 6.5 more minutes, but I still have to justify the subtitle of my title, so stack again. So at the very beginning we had this kind of magic machinery where we put in some stack and got a infinity ring spectrum, which actually doesn't work quite as well as it say. Okay, but there's actually a way to go back. So if we have a homotopy commutative ring spectrum, spectrum R, we can also always associate a stack with this.
So do you mean by that an E2 ring spectrum?
No, I mean a monoid, commutative monoid in the stable homotopy categories. Yeah, with respect to smash product. So just homotopy commutative. Stack X with a map, or actually an affine map if you want. If you know what this means, from X to MFG. Let me give. I think this construction is probably due to Hopkins, but I don't quite know the history here. And just to give you a flavor, how I mean this, how this goes is, you take mu star of R, actually just the even guys, and I mean this is an mu star mu co-module. And it turns out that, and graded to be precise, it turns out graded mu star mu co-modules are equivalent to quasi-coherent sheaves on the modular stack of formal groups. So, and I think if you have never seen this, a great place to learn about this this paper by Nico Naumann on the modular stack of formal groups in stable homotopy theory. But actually I forgot something, namely the ring structure. There's actually has an algebra structure here, and we get an algebra structure here. So I guess I could. And then there's a construction called relative spec, where I have a quasi-coherent commutative algebra. I can associate something, you know, like a commutative ring, I get a scheme, and I can do this in a relative way. So if I have commutative quasi-coherent commutative algebra on something, I can do a relative spec and get such a map. Okay, and okay, time is running really short. Let's give some examples. So if the easiest thing is R is even periodic, let's call this XR. Then the stack just happens to be spec pi 0 of R, and the map classifies exactly the formal group of this guy. So this is nice that we get this back. A more surprising thing is that X TMF is the modular stack of elliptic curves. So we get this guy back. So I guess this is, if I have to guess, this is due to Hopkins. I mean, must be, I guess. Actually, I mean, this in particular gives that if I take X TMF1n, and let's be on the careful side, I mean, that is always true. So you can deduce from this thing that this, I mean, this happens to be an affine scheme for n bigger or equal to 4. This is even periodic for n bigger than 4. Then at least in this case, you can deduce it from this, but actually, this is always true. And actually, this is also, if I take TMF0 and this is a stack which I think didn't introduce, but is similar to the M1 and get exactly what you expect. Yeah, I mean, I don't think this is anywhere really written down, but let's say it's due to a Q. And okay. And what is nice is you can actually also say something about this little TMF. Hopkins again, so there's a variant of modular stack elliptic curves. So if you've seen elliptic curves, you've seen probably that you can present them by cubic curves, and this would be all cubic curves here. So, and just a question, and you can show that this compactifications of modular stack with level structures can be obtained by certain normalization construction, which I don't really want to explain, but I just want to make kind of, I think my time is up, but maybe let me at least make this one point, that so can show that x little TMF1n is m1n cube, where this is defined by some normalization. Procedure, which is completely algebraic procedure, and so hypothesis or guess, one can do a similar construction called m0n cube, that we have such an equivalence, but if TMF0n is defined correctly. So one has to make care what one actually means by this, and this is true at least in one non-trivial case if n equals 7 at the point 3. This is again based on our decomposition results. And I'm not sure it's true for n equals 3, and this would be the really kind of test case to know whether there's any chance to be true in general. Okay, thank you.
Questions?
In this last one, does this sort of say that little TMF1n is then the ring of integers and TMF with a capital?
Okay, so I mean the normalization procedure is one takes, so to speak, the normalization of this guy in this guy. So this would be kind of like corresponds to a periodic guy. So in this sense, it would be in some sense the ring of integers in yeah. So one could say that if this is like the integers and this is like some number field, so then this would be okay. Yes, this is perspective. But I'm not sure how to define this topologically without